Hi guys, so I'm gonna start a new playlist for to help students who have to take the MCAT or just for students who need an introduction to thermodynamics. And today I'm gonna talk about temperature scale, and then next time I will talk about heat and specific heat. So the slides I'm using come from this book here. So it's a algebra-based physics book. And for the conceptual ideas here, I am using those books here. Some of the slides also come from that book here by Paul Hewitt. Okay, so this part is very easy. You already know the three temperature scales. So most of the world is using this temperature scale, which is in Celsius. So it's using two arbitrary points here. 0 degrees Celsius, which is ice, freezing point, and 100 Celsius, which is when water turns into steam, so boiling point of water. And then we have the Fahrenheit scale that we are using in the US, which doesn't make a lot of sense, but nevertheless, you have to know it. So it's also using 2 points here, 32 degrees Fahrenheit, okay, which is the freezing point of water, 212 degrees Fahrenheit, which is the boiling point of water. And initially, Fahrenheit, when he developed his scale, he was using also 2 points, but they were different. He was using the temperature of human body, which of course can change if you are running a fever or not, which is about 98.6 Fahrenheit. If 98.6 Fahrenheit, if you're not running a fever, and he was using the temperature of ice plus salt. Okay, so and then you changed the 2 points, so it's now it's matching the 2 points on the Celsius scale. So the first thing you can see here, and that's how you don't need to memorize the relationship between Celsius and Fahrenheit, is that between 0 and 100 degrees, you have 100 steps. Okay, so it's a centigrade scale. Here you have 180 steps. So the relationship here, it's going to be 9/5 or about 1.8. So it means that one step here, so one degree step here will be about 2 degrees step there. Okay, so a step of 2 degrees Fahrenheit is about a step of 1 degree Celsius. Okay, so using those 2 points here, the 2 points there, you can derive the relationship without memorizing. So Fahrenheit is here, Celsius is there. So you see 0 degrees Celsius here, it's gonna be 32 Fahrenheit. Okay, so you want to do it this way. So that's gonna be your y-intercept. Here you have 100 degrees Celsius, which is about 212. So it's not on scale, but here it's gonna be 212. Okay. So it's easy to derive the linear relationship here. Remember, y equals mx plus b. So the y-intercept is 32. And then you see the slope is rise over run. So the run here is 100, the rise is 180. So the slope will be 180 over 100. which is 9/5. Okay, or 32 plus 1.8. Okay, so easy. One thing to remember is to get a sense of the Fahrenheit scale is that room temperature here is about 20 degrees Celsius or about 70 degrees Fahrenheit, about. Another thing is that the only thing they have in common here is minus 40 degrees Fahrenheit is minus 40 degrees Celsius. Okay, it will be the same temperature. So minus 40 degrees Fahrenheit is minus 40 degrees Celsius. Okay, so then we'll talk about that, but we have the Kelvin scale, okay, which is same as Celsius, but shifted by 273.15. So that means that Celsius, okay, it's going to be Kelvin minus 273.15. Okay, or Kelvin is Celsius plus 273.15. So 1 degree, a step of 1 degree here, Celsius equals to a step of 1 degrees Kelvin. Just a vertical shift. Okay, so you need two arbitrary points here. So that's for the centigrade scale. That's for the Fahrenheit scale. Okay, so here is a easy example. If you don't run a fever, usually your temperature will be about 98.6 Fahrenheit. Can you convert that in degrees Celsius? Okay, so that's super easy. So Fahrenheit is y-intercept 32 plus the slope. That will be degrees Celsius. So that's going to be 98.6. And you can solve for degree Celsius. And you should find equals to 37. So if you are healthy. If it's above 37, so you are running a fever. So the math is easy. Okay, you can do the same. Sorry. You can do the same here if the temperature is minus 20 degrees Celsius. So again, Fahrenheit is the y-intercept plus the slope. And here you have Celsius. Now you have to be careful. That's going to be a negative 20. And you can solve for the Fahrenheit. Okay, so you can stop the slide or the video. And that's what you should get. Okay, so then we have the Kelvin temperature scale. So that was developed in the 19th century by William Thomson. I think William Thomson, it's Lord Kelvin. William Thomson, who was Lord Kelvin. So that was when thermodynamics was developed with the thermodynamics law, the industrial revolution. So it's an absolute temperature scale, and they are using that absolute zero here. So at that temperature here, everything will reach its lowest energy level. We cannot reach it though. But if we were able to reach it, so then very weird quantum effect will take place and the energy will be the lowest possible. And you see, it's just a shift, right? temperature Kelvin is temperature Celsius plus 273.15. So you're using that in thermodynamics, or if you are taking a class in astronomy, for example, and if you study what it's called the black body, it says, like, let's say you have a star emitting light. So it could be like our sun emits infrared, it's going to emit visible light, it's going to emit ultraviolet, X-rays. So all kind of colors, but it's going to have a peak wavelength. Okay? And the peak wavelength is going to be in the green. So it means that most of the photons that our sun is emitting are green photons. Okay, so here you have the photosphere, and you have a very simple relationship, which is called Wien's law, between the temperature here, temperature of our sun, not inside the core, but the outside temperature, and the peak wavelength. Very simple relationship. So it's just an example how you're going to use that temperature in Kelvin. So it says that the peak temperature of a star or an incandescent bulb, for example, will be equals to a constant divided by the temperature in Kelvin. That constant here is about, I'm going to simplify, 3 times 10 to the negative 3 meter Kelvin. So, and the temperature of the sun, let's say it's about 6,000 Kelvin. So the question is, can you find the peak wavelength of the sun? Okay, so it means you have light coming from the sun, and then you have the light going through a prism. So you're going to have a rainbow. What's the color, the visible color that with the most photons, the most intense, with the most intensity? Which color? Okay, so can you try to do this? It's going to be easy. So the wavelength will be, it's about 3 times 10 to the negative 3 over 3,000. Okay, so if you are good at math, you see 3 divided by 6 is 0.5. So 0.5 times 10 to the negative 3 divided by 1,000, it's going to be 5 times 10 to the negative 7 meters. Otherwise, you can use your TI, 3 times 10 to the negative 3, divide by 6,000, it's going to be 5 times 10 to the negative 7, so it's a review of scientific notation. And if you want to convert that to nanometers, can you do that? So 1 nanometer is about 10 to the negative 9 meters. So you can cross multiply, divide, and you can pause the video, and you're gonna get 500 nanometers. And then you can use your equation sheet. And if you use your equation sheet, you see that 500 is a kind of green. Okay, wavelength. The unit is nanometer, not to confuse with the frequency. So frequency here is in terahertz, which is 10 to the 12. So you have green, that will be the wavelength range, and that will be the frequency range. Okay, so that was also just an example. In astronomy as well, you use another law called Stefan Boltzmann law. And it says that the amount of energy emitted by a star, okay, will be energy per unit second per unit area. So power per unit area will be proportional to the temperature to the fourth power. Okay, so the energy emitted per unit second per unit area is proportional to the fourth power. And you are using temperature in Kelvin. So these are two examples you could find because it's very simple applications. Okay. So to measure temperature, we can use the change of properties of materials as a function of temperature. So here you have, for example, a gas thermometer, which is not used in everyday life. So it will be used for extreme temperatures or for specific scientific experiments or to calibrate other thermometers. So the principle is very simple. So you take a gas here, and as the temperature increases, the volume is not constant. The pressure is constant, but not the volume. So as the temperature increases, like it's a Gay-Lussac law, as the temperature increases, the volume it's going to increase. The pressure stays the same, so the mercury level here it's going to increase. So that's one way to do it, but it's only in cases when we need very accurate measurements. Okay. About the Kelvin scale, again, you see that if now you are taking, you can use what's called Charles' law. Okay, so you can have a given volume. So the volume of a gas, ideal gas, does not change. You see that the pressure inside the gas, as you increase the temperature, is going to increase also. For a specific gas, as if the pressure is multiplied by 2, for example, the temperature will be multiplied by 2. Okay, and you can do the same experiment for different gases. And if you extrapolate here, that's what we call the absolute zero. Okay, so you see there is proportion. It's proportional pressure here is proportional to temperature. Okay, when you are using ideal gas. So pressure is proportional to temperature for a given volume. And when you extrapolate those lines here, they're going to meet at that point here, that absolute zero. That's how Lord Kelvin, define his or develop his temperature scale. Okay, so other thermometers that we are using today, again, depends on the change of properties of materials. So for example, this is called a thermocouple. So turns out if you have two different metal, okay, their voltage, the voltage between them, the electric voltage, will depends on their temperature. So this is very nice if you are working with microcontroller, if you are doing electronics. It's very easy to measure thermometer when you want to read a sensor, for example. Then you're gonna use such device. Okay, so it's an inducer because the voltage, okay, depends on the property, the material property. Okay, so the temperature depends on um, the voltage between these two metals. Okay, so here are some examples. So the thermometer that we use to find out if we are running a fever or not. Here we put that in the ears, and it's so here it depends on the radiation we are emitting, because we are emitting infrared, and the wavelength, the peak wavelength of these infrared radiations depends on the temperature. So actually it's using Wien's law again. Okay, so if you know exactly what is the wavelength of the infrared we are emitting, you can find the temperature. Another property you can also use, property change that we can use, is if we have two kinds of metal. Okay, so bimetallic device, so two kinds of metal, one will expand more than the other one for a given temperature. Okay, so it means if you have two metal, so it's called a bimetallic metal, okay, one on top of each other. If you increase the temperature, so that metal here will expand more and it's going to bend in this direction. So I have found interesting website here that shows you how it works. Here. See, so this is just one metal, and as you increase the temperature, you see it's going to bend, okay, because it's going to expand in one dimension. And it's you see, you can really use that as even as a way to measure the temperature here. Now we can use that to make those thermometer that you find everywhere. So it has two metal, like those two. Okay, so it's a bimetallic metal. And when you increase the temperature, the spiral here, it's gonna expand, and the needle, the needle here, the pointer, is gonna move that way. And again, in this website, they're gonna show you. You see how it's expanding, the spiral is expanding, and then it's cooling down, it's contracting again. So that's how we can use that in thermometer, but also in thermostat. See? You see how it works here? So if the temperature increases, that thing is going to expand, and that pointer is going to move in this direction. See the kind of thermometer you can put in your turkey, for example. Okay. They use that also for thermostats. Okay, so this it's a very simple and smart device. Okay, so in the room, you can use that technology to make sure the temperature stays the way you want. Because if the pointer is moving, there will be an electric connection that will open up, and the heater will stop working. You can use also electric resistance. Okay, so the electric resistance can also change as a function of temperature. So in that case, usually we use semiconductor. As the temperature increases for semiconductor, the resistance decreases. Or you can use mercury or alcohol, and you see that as you increase the temperature, the mercury here, alcohol, I don't know, is going to expand by a tiny bit, but a tiny bit in 3D expansion will be translated in the large increase here in temperature. Okay, so I don't know if I have, you see, something that kids will do back then, increasing the temperature of mercury, and then the top will pop out. Not to repeat, not an experiment to repeat. Okay? So temperature, of course, is a way to measure how hot something is or how warm, but if you look at the microscopic level, there is a more formal definition. Temperature is actually the average kinetic energy per molecule. Okay? And not any kind of kinetic energy. It has to be translational kinetic energy. So all the molecules in the material, they move around, they jiggle around, they shake, right? They are always in random motion. And the temperature is the average kinetic energy of those molecules. So as you increase the temperature, the molecules are going to move faster, okay? And the kinetic energy, the translational kinetic energy is going to increase as well. Okay? So this is actually, so it's at a microscopic level. The temperature is proportional to the average translational kinetic energy per molecule, okay, or per particle. Okay, so it depends how fast the gas particles are bouncing or how fast the liquid particles are sliding past each other. And in the solid is how fast molecules are moving or vibrating. Okay, so if you have this equation, higher temperature means what? That body A has more, so that will be kinetic energy per particle. Okay, so when we talk about internal energy, it could be both kinetic energy, the three kinds of kinetic energy, and potential energy. Okay, so that's just a parenthesis. It comes from the book Physics Behind the Headline. And you see that if two materials have the same temperature, that means that they have the same kinetic energy per molecule, but it doesn't mean that the molecule have the same speed because it depends on the mass. So again, here, if you use temperature in Kelvin, you have a very simple relationship between temperature of material and the kinetic energy per molecule. See, it's a very simple relationship. Now, if there is a simple demo, okay, you see here that, let's say, these are molecules and they don't have the same mass, but you're going to shake them the same way. So they're going to have the same kinetic energy. You're going to see that they do not have the same speed because they don't have the same mass. See that the smaller one are going to be faster than the bigger one.
What you might be able to sense if you watch this for, a few hours, is that can actually be mesmerizing, is that the big balls aren't moving as fast on average. Sometimes they get a big kick and they go flying, but on average they're kind of slow, and the little ones are moving faster.
So you see you have this relationship. Okay, so we're talking about kinetic energy and not speed, okay, because it also depends on inertia and on the mass. But anyway, same